Well, I thought we would start this video on friction without paper, because friction is about surfaces, and I've got some nice carpeting for here. This is some really interesting carpeting. It looks like hair sticking out of there. So what I thought I'd do is I'd take this other carpeting and flip it over so that the carpeting is touching the carpeting. And now I want to show you something cool. If I pull, I want to do no funny business right here. I'm going to pull this top carpeting, and I want you to notice that the bottom carpeting comes with it. So whatever friction is, it's probably more between this carpeting and that carpeting than it is between the bottom of this carpeting and the table. So this is pretty slick, but this, and you can hear it's a little bit louder, is a lot more friction. And you can think of some other things that are low friction or high friction. In particular, I'm thinking of, well, something low friction. You can think of like pieces of plastic sliding against each other, really low friction. Actually, pieces of plastic sliding against carpet are also pretty low friction. And you might think of a sled in the snow, pretty low friction, or some other stuff, pretty low friction. That's where I want you to be thinking about things. But I was thinking about other things that have a lot of friction, like this material is designed to go in the bottom of drawers in your cabinetry, for instance. So what I think is cool is that if I now pull this, see, watch that. I set the carpeting on the cabinetry sticky stuff. Now I'm going to put this guy right here on it. Get ready. And I'm going to pull just the top. No funny business. I'm way over to the right now, but notice, dang, the top pulls off now. So what we can conclude, and I have to like really scoot this stuff, is that the friction between this carpet and that carpet is less than the friction between the bottom of this and the sticky stuff, and the bottom of the sticky stuff and the table. So this sticky stuff is really sticky. I could like shake the whole table with this. You can see the camera's shaking a little bit. Who else might be really interested in getting really high frictions? Well, how about tire companies? Very interested in friction. So if you work at a tire company, I would be interested if you would get the friction on my tires and the road up really, really high. It's interesting though, I have to say the friction between my tires and the road. I can't just say the friction of my tires, because my tires on ice won't have the same friction as my tires on the road. So that's why it's important to stay on the road and not ice. Or gravel, also really low friction on gravel. And marbles, when I drive on marbles, I also don't get a lot of friction. Oh, some people call friction traction. I hope that's okay with you. I'll just make you a little cool slide. Friction equals traction. And if you're thinking, I need a lot of traction, then you're thinking you need a lot of friction. This comes from the root of the word tractor also, which has something to do with pulling. So tractor pulls are fun, but they're redundant. Of course a tractor pulls, because a tractor, great, okay. So friction, though, enables you to do pulling with a tractor because of traction. I don't want to talk about it anymore. So I want to kind of get you to the idea of a microscopic basis of friction. Here are two surfaces that might not have very much friction between each other. And I drew them kind of slick-like so that you can imagine there's not much interaction between these surfaces. They're just sliding on top of each other. So a nice bit of plastic sliding on a nice bit of plastic is not much friction. Boy, this is really boring so far. Okay, well, what if I give you a piece of carpet and it's like, you know, twisty nasty on top and some kind of cool carpety way, and I give you another piece of carpet and it's like twisty nasty on the bottom because I turned it upside down in some kind of twisty nasty kind of way. And I pull this guy, and I just get a force on here, and I pull, maybe I tract, you know, like a tractor beam, sort of, because a tractor beam just pulls, right? So I'm going to pull this carpet, and I'm going to hold this carpet that direction. Maybe I'm shearing the relationship between them. Go watch another video. I don't want to talk about that either. But I want to try to talk to you about what's happening with these little bits of carpeting stuff. Man, I do not have the right vocabulary to teach this. But I think that these guys, these little infrared guys, will be bent a little bit to the right. as this pulling happens, right? But then, as soon as one passes by, it'll spring back to where it is. So, like, think of like this. I'm sliding these guys relative to each other. Those guys get pulled back, and these guys get pulled to the, wow, I guess they get pulled way to their right. These guys get pulled way to their left. And then they snap back. And those are sort of like inelastic collisions, because as they snap back, they just shake a little bit, and that energy generally goes to random vibrations inside of here. You know what random vibrations are? I do. So, friction is stealing useful mechanical energy and turning it into non-mechanical energy in the form of heat, because it's creating random vibrations. And this is happening in a very illustratable way in carpeting, but it's also happening even as I slide my finger across the paper. There are little bits of paper, even little molecules for even smoother substances that are bending just a little bit, and then as soon as my hand goes by, they can relax back, and that shaking becomes a random vibration, which is, well, heat. All right. And now I want to talk to you a little bit about kinetic friction. Kinetic friction is not very bad. If you take a cat and you push a cat this direction and the cat moves steadily, then the cat is in equilibrium. So I'm going to do a side view of that adventure, and I saw a purple fuzzy lump. I don't know what you thought you saw, but I'm going to draw mg. That's the force of gravity on that cat. And I know there are other forces on the cat, like, for instance, the normal force is pointing up, and I'm kind of thinking that the normal force is equal to mg. And here's why I'm thinking that. Do you want me to tell you why? I'm thinking that because the cat is in equilibrium. There's no physical law that says those guys have to be equal, but when I'm looking at a cat, I'm thinking, cat, you're not doing anything. It's just a stupid sleeping cat. Cat, cat, yep, just sitting there. So the force up on it must be equal to the force down on it because it's not feeling any net force in the y direction. So let's write that out. I'm going to say that the net force in the y direction is mass times acceleration in the y direction. Sure, and I'm not putting vector hats on there because I've already said in the y direction. But, oh, I need to define the y direction. Oh, it's that way. Sure, normal, right? So mass times acceleration in the y direction is 0 because there's no acceleration in the y direction. There's a force up in the y direction. That's the normal force. Notice how I don't put a vector hat on it because now I've said that it is in the positive y direction. And then I have to subtract mg. This is a brand new equation that we just made, and we can use it. We can use it to learn about our situation. Let's do that later, though. The next thing I want to do is finish making this free body diagram. The free body diagram also has forces. Which way was I pushing the cat? I was pushing the cat that way. And I'm going to say that the applied force was the force that I was exerting on the cat, that direction. Beep. And the cat didn't speed up. Did you notice that? The cat was just going at the same velocity the entire time. That means that there cannot have been a net force on the cat. In fact, what I'm trying to say is the cat was in equilibrium. Not only in the y direction, that's the statement right here of equilibrium, but also in the x direction. Equilibrium is a very powerful condition, so I know there must have been a force backward on the cat, and that's that force that I'm going to call friction. This is the force of kinetic friction because it's moving. The cat is moving relative to the surface that's exerting the frictional force on it. As the cat goes left, friction points to the right. Okay, so here's my statement of net force in the x direction, mass times acceleration in the x direction, and I declare that the acceleration in the x direction is 0. And I notice that there are two forces in the x direction. One of them is positive, that's the force of kinetic friction, so I write Fk here, and it's to the right, which is my x direction, so I leave it as positive with no vector hat. And the applied force is to the left, so I have to subtract the strength of the applied force. No vector hat again. This is another new equation that we created by applying Newton's second law. So when you get a situation, you finish drawing your free body diagram, immediately apply Newton's second law in both dimensions. This guy right here is a very simple equation that you can solve. You can solve this too. It says the normal force is mg. Awesome. And this equation is a very simple equation also. It says the force of kinetic friction is the applied force. These situations are not always true. These results come from the fact that we have equilibrium and there aren't any other weird forces or weird angles. So this is a very simple introduction. These should not be taken as always true at all. These, oh, this and that, haha, those are always true. Awesome. But these guys right here are a special case for our simple situation. Now, we want to kind of relate these forces. Like, I want to know why the force of kinetic friction has a certain value. And it probably has something to do with the bottom of this cat and the character of that paper. And somehow, as they interact, there's a frictional force that develops. I don't know, fibers bending or something. I don't even know if we need to go to that level anymore. But I do want to say, what do I want to say? I want to say something about something that's going to describe the relationship between how hard, would you believe that if I push down on this cat, it's going to be harder to slide it? Wow, it's a lot harder to slide it as I push down on the cat. When I push down on the cat, I'm increasing the force between the paper and the cat, which we could call the normal force. That force of interaction between the paper and the cat is very big. Another way you can try this at home, clear off a little bit of space in front of your computer. I don't know what you're doing with all that crap all over the place. Just clear out some space, take your finger and slide it gently across the desk. And now try push down and try sliding it. It's a lot harder when you're pushing down. It may even heat up. So you're noticing firsthand that friction creates heat. So you could light your hand on fire if you continue doing that. I don't recommend it though. I'm just kidding, you can't do that. But you'll hurt yourself. That's funny. Now, if these forces are related, like the force of friction is related to how much the ground is pushing up on the cat. Not so much related to mg, but in this case mg is how much the ground is pushing up on the cat. Those two guys are related, and I'm gonna define this variable called mu sub k, and that is how much the friction force is divided by how much the normal force is. I want you to think about the units of mu sub k, and if you have some cool ideas, you can put those in the comments, but it's the force of friction divided by the normal force. It's that ratio right there. And what if we wanted to know how big the force of friction was? We could just solve that. We could say the force of kinetic friction is mu sub k times the normal force. And in my experiments, I have always found mu to be in between 0 and 1. Mu sub k happens to be in between 0 and 1. There are some tire companies that claim to have mu's higher than 1. What? Well, maybe if like the asphalt is like this and the rubber of the tire somehow fills all of those grooves, maybe if it were like hot rubber. Oh, you know you can increase traction on your tires by spinning them initially too. So race car drivers will get really low tires and they'll spin them a little bit so they get hot and like sticky. Yeah, that's where you get all that force. And you want that force so that you can cause the car to go that direction. It looks like a melting eyeball. Sorry about that. Thinking about things. But I was thinking about other things that have a lot of friction, like this material is designed to go in the bottom of drawers in your cabinetry, for instance. So what I think is cool is that if I now pull this, see, watch that. I set the carpeting on the cabinetry sticky stuff. Now I'm gonna put this guy right here. Well, I thought we would start this video on friction without paper, because friction is about surfaces, and I've got some nice carpeting for here. This is some really interesting carpeting. It looks like hair sticking out of there. So what I thought I'd do is I'd take this other carpeting and flip it over so that the carpeting is touching the carpeting. And now I want to show you something cool. If I pull, I want to do no funny business right here. On it, get ready. And I'm gonna pull just the top. No funny business, I'm way over to the right now, but notice, dang, the top pulls off now. So, what we can conclude, and I have to like really scoot this stuff, is that the friction between this carpet and that carpet is less than the friction between the bottom of this and the sticky stuff and the bottom of the sticky. Some other things that are low friction or high friction, in particular, I'm thinking of, well, something low friction. You can think of like pieces of plastic sliding against each other, really low friction. Actually, pieces of plastic sliding against carpet are also pretty low friction. And you might think of a sled in the snow, pretty low friction, or some other stuff, pretty low friction. That's where I want you to be there. I'm gonna pull this top carpeting, and I want you to notice that the bottom carpeting comes with it. So whatever friction is, it's probably more between this carpeting and that carpeting than it is between the bottom of this carpeting and the table. So this is pretty slick, but this, and you can hear it's a little bit louder, is a lot more friction. And you can think of